So last time we talked about path connectedness. We showed that path connectedness implies connectedness, and we gave a counterexample of a space which is connected, but it's not path connected. That counterexample was the topologist sine curve, which is the graph of sine over 1 over x, and then taking the closure of that graph in the inside the plane, right? When you equip that graph with the subspace topology, you get this space, which is a curve that oscillates infinitely many times as it approaches the y-axis, and then you adjoin. When you take the closure, you adjoin the y-axis from -1 to 1, right? And the resulting space is connected, but it's not path connected. So now we start discussing compact spaces or compact spaces. So this is another example of a topological property, namely a property that it's invariant under continuous maps, right? The image of a compact space under a continuous map will be compact. You might have seen this property in analysis and calculus. It's some sort of finiteness property, right? So in analysis, you prove this theorem. You first introduce a notion of compactness, usually in the Euclidean space, and then you prove that closed and bounded subsets are compact, right? For those of you who have taken analysis. So you can think of compact, yeah. Yeah, so that's an analysis. And then, I mean, this notion took a while to develop. First of all, I think mathematicians thought that the correct notion was that a space is compact if any infinite collection of points has a limit point. But it turned out that the correct notion was a stronger notion that would work in more general settings. These two agree under certain hypotheses. So compactness is some kind of finiteness notion for topological spaces. So let me go ahead and define it. So first, let me say what a cover or a covering of a topological space is. So a collection curly A of open sets in a topological space. Sorry. Maybe I should say of sets. So of subsets. So a collection curly A of subsets in a topological space X is said to cover X, or to be a covering of X, is the union of all the elements of A is equal to X, right? So it's just patching a bunch of subsets that cover your whole space. That's a covering, right? This collection has no, this notion has no bounds in its cardinality, right? It can be very big, or it can be finite, or whatever. X is an open cover of itself, right? So good. A cover of itself. Now we say a cover is an open covering if its elements are open sets in X, right? So A is a collection of open sets, maybe U alpha, where alpha is given by some the alphas are indexed by some set, some indexing set. If all of these elements are open, and if the union of all of these is X, then we say that collection is an open cover or open covering. Okay. And now a space is compact if every open covering has a finite subcollection that also covers X. Okay. If I give you any open covering, if you can always find a finite subcollection that covers your space, then we say the space is compact. This is a very important notion in topology and mathematics and in analysis. Is this clear? Does this make sense? Any questions about the definition? It has to be very clear what it means. We also say a space is compact if every open cover has a finite subcovering. Okay. Okay. First example, are the real numbers with the standard topology is not a compact space. Why? Because I can find an open covering which does not have any finite subcover. So there are many such open coverings, but I can take the following. I can take this collection of open intervals. So I take the open interval from n to n plus 2, where n is an integer, right? These, of course, cover all of R, right? Because they subsequent ones have an overlap. However, I cannot cover all of R with a finite subcollection of these, right? I'll always leave infinitely large gap, actually, right? So these look like the following. So you can take like from 0 to 2 is one open set. Then the next one goes from 1 to 3. The next one goes from 2 to 4, and so on, right? It's like a chain of intervals covering the real line. But of course, there's no finite subcollection of these that will cover the whole line, right? Like if you take a finite subcollection of these, there will be a maximum and a minimum n, right? So after that point, you won't be able to cover anything else. So does that make sense? So R is not compact. Let's give an example of a compact space. So suppose you take the following set of points with the subspace topology induced by R. So this is an infinite set. So you take 0, right? You take 0, and then you take 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. So that infinite collection of points together with 0. I claim this is compact. Okay, as a subspace of the real numbers. Even if it's an infinite set, it's compact. Okay, so let's prove that formally. So suppose we have any open covering of X, curly A, right? we want to prove that any such a thing has a finite subcovering, right? So let A, curly A, be an open covering of X. So in particular, since A, all the elements, the union of all the elements of A equals to X, there has to be some open set U containing 0, right? So since 0 is a limit point of the sequence, that means that there is some capital N such that 1 over little n lies inside U for all little n greater than that capital N, right? This is 0. You take an open set around, maybe do it like that. This is 0. You take an open set around 0, right? Then that open set contains all but finitely many points in this sequence 1 over n, right? So all but finitely many points. So you have an infinite number of points inside here, and then you have a finite number of points outside, right? That's true for any open set containing 0. Good. So I now can find a finite subcovering. I take U, and I take U, and then I take an open set in A for each of these finite number of points outside. And that will be my resulting finite subcover of A, which covers the whole thing. So let me say that a little bit more formally. So there is some U containing 0, but then that U contains all except finitely many points in the sequence 1 over n. So suppose these are the ones that are left outside U, right? Each of these points are contained in some U1, U2, and up to UN, because A covers all of X, right? So now this collection, U together with U1, U2, up to UN, is a finite subcovering of X. Done. So X is compact. Any covering has a finite subcover. Any open cover has a finite subcover. Okay. Any space containing only a finite number of points is compact. This should be straightforward. Maybe more interestingly, the half-open interval, or any half-open interval, is not compact, right? In particular, the half-open interval from 0, not including 0, to 1, including 1, is not compact. We can take the following collection of open sets. This is a covering, an open covering of the half-open interval with the subspace topology. Do you guys agree that this is an open covering? And it has no finite subcover, right? If you take any finite subcollection of this A, you will leave some gap, right? There will be a maximum n, and then everything from that maximum n to 0 is not covered. All those points in between, right? The picture is this is 0, there's 0, and this is 1. Then you're taking these sets, right? 1/2, 1/3, and so on. They're nested, right? But that does not contain a finite subcover. Any finite collection will have a maximum n, right? And everything after that, or everything before that, between 0 and that maximum n, that 1 over n for the maximum n, will not be covered. So this is not compact in the subspace topology of the real numbers.
So our notion that you said we've had before, maybe that of closed and bounded.
Uh-huh.
Bounded is not a topological property, is it? It's something that we only have in metrizable spaces. Is that correct?
Correct. Yes.
So in a metrizable space, that would be I'm guessing that a definition is equivalent, but it's obviously not sufficient for non-metrizable spaces.
Yes, we will prove this. Yeah. We will prove this. We will also prove that in a metrizable space, we have another notion of compactness, which is a space is compact if any infinite sequence of points has a limit point. Yeah.
So my question, I guess, is then, are we going to find out, though, that all compact spaces are, in fact, closed in any setting? Or are there exceptions where you can have an open set that is compact in some setting? Aside from maybe, or a set that is not closed, that is still compact in some setting.
A set that is not closed. Yes, we will have examples of this in non-metrizable spaces. Yeah. Good question. Yeah. We will give counterexamples on Friday, I think. Yeah. Actually, maybe today if we have, yeah, maybe not. Okay. Good. Actually, let me say something. You asked for, there are two things, boundness and closeness, right? Boundness is related to the metrizability. Closeness is not related to the metrizability, right? So for boundness, we will have counterexamples regarding the metrizability, of course. I mean, that only makes sense when you have a metric, and that's not a topological property, as you say. Then closeness is different. A compact space might not be closed, but in a Hausdorff space is closed. So, yeah, that's in most cases that you think of in geometry and topology, compact spaces will be closed. But in algebraic geometry, you have plenty of non-Hausdorff spaces, which are interesting and important. Okay? So you need the Hausdorffness condition. That's a sufficient condition to show that a compact space is closed. That, I think, we'll prove today if we have time. Okay? The boundless conditions we will treat next class or next week. Okay, good. So a lemma regarding subspaces. So this is a straightforward lemma. So let's just state it and quickly prove it. So let X be a topological space and let Y be a subspace. Then Y is compact if and only if every covering of Y by sets which are open in X contains a finite subcollection covering Y. So what's the difference between this and the definition of compactness? That I'm taking this covering to be open sets in X, right? That's straightforward, right? You guys see the proof, kind of? Subspaces, the open sets in the subspace are given by intersecting open sets in the bigger space with the subspace, right? With the subset Y. So that's, you translate what it means to be compact using this kind of the definition of the open sets, right? So let's just quickly go through it. So suppose Y is compact and A is the covering of Y by open sets in X. I want to show that there's a finite covering of open sets in X covering Y, right? So I look at the intersections of each of the open sets with Y. These are a covering by open sets in Y, right? By the definition of the subspace topology, each of these is open in Y. And they cover Y because the A alphas cover Y, right? But since Y is compact, there's a finite subcovering. So I can forget about the intersections and I get this finite subcollection of A covering Y. And each of these are open sets in X, right? Now the converse is similar. So suppose the given condition holds, namely every covering of Y by open sets in X contains a finite subcollection covering Y. So suppose that condition holds, and suppose this is an open covering of Y where each B alpha is now open in Y, right? Assuming the condition for open sets in X, I want to show that Y is compact, namely that I can find a finite subcollection of this B. So for each alpha, there exists some A alpha open in X such that the intersection of A alpha with Y gives you B alpha, right? Because these B alphas are open in Y. What does that mean by definition? That there exists an open set in X such that when you intersect it with Y, you get B alpha. That's the definition of open sets in the subspace topology, right? So I can always find these A alphas for each B alpha. And now I just take this collection that covers Y because the B alphas covered Y. And all of these are open in X. So by hypothesis, there's a finite subcover of those. And then I just take the corresponding elements in the collection B, right? Corresponding to these indices. These will cover Y as well because all of these cover Y, right? And this is a finite subcollection of B. This is a straightforward lemma, just expressing what compactness means in terms of the definition of the subspace topology. In terms of the definition of the open sets in the subspace topology, right? Okay, so whenever we introduce a notion, we prove that this notion is compatible with some of our constructions or definitions that we have introduced previously, right? Just like how we did with connectedness. We explored how it relates to taking products, to taking subspaces, and so on. So we do the same with compactness, okay? And these are the 4 claims that I will try to show today. So first, a closed subspace of a compact space is compact. Second, every compact subspace of a Hausdorff space is closed. I think this is what I was telling Michael earlier. The image of a compact space under a continuous map is compact, and the product of finitely many compact spaces is compact. You should like go to bed repeating these, right? Every closed subspace of a compact space is compact. Every compact subspace of a Hausdorff space is closed. The image of a compact space is under a continuous map is compact, and the product of finitely many compact spaces is compact. Are the statements clear? In fact, this will be true for an infinite product in the product topology. But that's kind of hard to prove. I mean, it's not hard, but it requires work. It's called Tikhonov's theorem. I'm not sure if we will prove it or not. It's in Munker's book. I mean, you guys know that the product topology and the box topology are tricky when you have infinite products, right? So, but it's doable. It's just hard to follow in a presentation. You'll be, yeah, it's easy to get lost in the details. Okay, so any questions about these statements? Okay, let's prove them. Let's prove one. So every closed subspace of a compact space is compact. So suppose Y is a closed subspace of a compact space X. I want to prove that Y is compact as well, right? So I assume I have a covering curly A of Y, an open covering, and I'm going to assume it's given by open sets in X. I can use the previous lemma, right? That if I find a finite subcollection of this, then I prove that that's the same as saying it's compact. You know, I can just look at open sets in X. That's what the previous lemma is saying, right? Because I can intersect them with Y. Okay, so suppose curly A is a covering of Y by open sets in X. So these are big open sets in X, a bunch of them, and Y is kind of behind all of those, right? Gets completely covered by all of those. So consider the following new collection, A prime. I take A and I adjoin the complement of Y in X. So everything that's not in Y. Since Y is closed by assumption, this is open, right? So I get a new collection of open sets. But these cover X, right? Because this covers Y by assumption, and this covers everything that is not in Y. This is an open set containing everything that is not in Y, right? So this covers X. And it's an open covering by assumption because we're assuming Y is closed. So by compactness of X, A prime has a finite subcovering. So if this finite collection happens to contain this guy, I just throw it out because I'm only interested in Y, in obtaining a finite collection covering Y. So if it's in that finite subcovering, I just throw it out and discard it. And the resulting collection is a finite subset of A covering Y, right? So I proved that Y is compact.
I always thought this proof was silly because like you union something that you were going to end up trashing.
Right, but you need to cover X, right? Because the assumption is that X is compact. Yeah. But yeah, I guess. Yeah. Okay. Now to answer one of Michael's question, every compact subspace of a Hausdorff space is closed. Every compact subspace of a Hausdorff space is closed. How would the proof go? I see. Okay, so suppose Y is compact and X is Hausdorff. I want to show that Y is closed, right? That's the same as showing the complement is open, right? So let x0, x0 be a point in the complement. We want to show that that complement is open. So for any x0, I want to find an open set U containing x0 such that it's contained in x minus y, right? That's the same as showing this x minus y is open if I do this for every point in x minus y, right? What does this mean? That U is contained in X minus Y. It's the same as saying U is disjoint from Y, right? So for each little y in the space big Y, I can choose an open set separating, I can choose two open sets separating x0 and y by the Hausdorff condition. And I can do this for all points in y, right? So I'm fixing x0 for a moment, and I'm going to look at all y, all little y's in y. For all of those, I have an open set uy, which contains x0, and an open set vy, which contains y, and they are disjoint for all y, right? Fixing x0 by the Hausdorff condition, right? And now I'm going to look at all of these vy's together. This is an open covering of y, right? Because y runs through all, I guess this is bad notation, right? I should keep using the same notation, which is something like that, right? This covers y because it runs through all points of y, right? But by assumption, y is compact. So there's a finite subcollection of these guys. Let's call them vy1 up to vyn, covering y, right? By compactness of y. So that means that this union, so since this finite collection covers y, that means that the union contains y. And moreover, this union is disjoint from the intersection of all the corresponding u's to each of these guys. Does that make sense? You kind of have to think about that for 20 seconds, right? If a point is here, it's in all of the u, u, y, i's in this intersection. But each of these is disjoint from each of these respectively, right? So a point here is disjoint from a point here, right? So what have we shown? We have shown that this U is an open set, being a finite intersection of open set. It contains x0 because all of these contain x0 by definition of the U's, remember? And U is open, and it's disjoint from Y. In other words, it's completely contained in this, it's contained in this complement. And this contains x0. So we have shown that this holds for any choice of x0. So in particular, that means that this complement is open. So that means that y is closed. So see how we used compactness here? We chose this finite collection, and now since this is a finite collection, this intersection would be open, right? Otherwise, I could not take an infinite intersection here and get an open set. So that shows that compact subspace of a Hausdorff space is closed. Any questions? Okay, 3, the image of a compact space under a continuous map is compact. This is equivalent to saying, if you have a continuous function, which is surjective, let's say continuous function from x to y, which is surjective, and X is compact, then Y is also compact. Is it clear that this is equivalent to what I said? If you have a continuous map which is surjective and the domain is compact, then the range is compact. Right? Since if we have an arbitrary map, we can just restrict the range to the image and get a surjective map. Okay, so let's prove that if you have a continuous map, which is surjective, and the domain is compact, then the range is compact. So suppose F is a continuous map from X to Y, which happens to be surjective, and the domain X is compact. Okay? Now, let U alpha be an open cover of Y. We want to prove that there's a finite subcover for the U alphas, right? Covering Y. Finite subcollection of the U alphas covering Y. Okay, so if I take the inverse images of these, I get what? I get a collection of open sets, because F is continuous, which covers X. Right? Since X is compact, I can find a finite subcollection covering X, or a finite subcover. Let's call the corresponding indices alpha 1 all the way up to alpha n. Okay. That's using compactness of X. And now, since Y equals f of X by surjectivity, right? And this is a finite collection of X, I can write f of X as what? As f of the union of the inverse images of these U alpha i's. But unions and images are compatible in the sense that the image of a union is the union of images. So I can bring this f inside, and I get the union of f inverse of the ui's, which is the same as the union of these ui's. So I've shown that Y is covered by this finite collection of open sets that I found using the compactness of X. So Y is compact, right?
Were we allowed to assume it was surjective?
Yes, this is what I said at the beginning. I'm saying this statement, the image of a compact subspace under a continuous map is compact, is equivalent to showing that if you have a continuous map between spaces, which is surjective, then if the domain is compact, the range is compact. Do you see that? I mean, you're just looking at the image under a continuous map. So with a loss of generality, you can just assume the map you start with is surjective, right? Because if you have an arbitrary map, then you can just restrict your map to the range, to the image and the range, right? And work with that. Yeah. You're just looking at the image. So, oops. Okay, and now the product of finitely many compact spaces is compact. So this requires a little bit of work. So let me show that if X and Y are compact, then X cross Y is compact. And then you would be done by induction, right? So this uses a little lemma which I will not prove now. Maybe next time, or maybe you can read the proof in the book. It's not hard, but so the lemma is the following. It's called the tube lemma. It's useful, very useful. It says the following: suppose X and Y are any topological spaces, and Y is compact. X doesn't have to be compact now, okay, for this lemma to hold. So suppose you have N, an open set in the product topology of X and Y. And suppose this open set contains this slice, right? Where x0 is some fixed point. So for example, I'm looking at y. I'm assuming y is compact, and I'm looking at x. X doesn't have to be compact. I look at the product of y and x, right? And I'm saying, suppose n is an open set. So n is given by this light blue thing like that, right? In this picture. N is an open set containing some slice. So the slice that I'm looking here is this line here, right? Where x0 is this point in x, right? So suppose n is an open set containing this copy of y, right? Then n contains some subset of the form w cross y, where w is an open set in x around x0. Okay? So given any n, open set in the product topology containing a slice like that, right? Not all open sets must contain a slice, right? You can have something that looks like that, right? That an open set could look like that. That does not contain a slice. By a slice, I just mean like a point in x cross y, right? So suppose n contains a slice, then I can find an open set in x such that the tube, or that open set cross y, is completely contained in n. That's called the tube lemma. Like if you look at a slice inside an open set, then there's always a tubular neighborhood. That's how we call it.
I'm not sure W has to be open. At least that's what the statement. I thought it was like when I first read this, I would have liked W to be open, but then like I was reading the statement in the book and I think if there was the proof, like yeah, that it's not necessarily open, this W.
Let me think. The proof. Maybe you're right. Let me see. No, I think yeah.
Says W is a neighborhood of X, not.
Yeah, W is a neighborhood of X. Yeah, you can take W to be open always. Yeah. By neighborhood.
Okay, so then like no, like word wise, like English neighborhood is like implying that it's open.
Yeah.
We're always assuming that. Okay, because like that was not clear.
Neighborhood
of
X
means open set around the point.
Yeah, that's a
You
definition.
could say open neighborhood, and that is clear. But if you just say neighborhood, you're just saying set around. That's what I'm understanding. But if we're implying that neighborhood implies open, that's fine.
Yeah, they defined it that way earlier.
Yeah, they defined it that way.
Okay, I don't recall.
But you can say open neighborhood or neighborhood. It means the same thing, even if it's confusing. Yeah. Yeah. So that's a tube lemma. Okay. Let me put this aside for a little bit. This uses compactness of y. Okay. Yeah, I can prove this on Friday, first thing. So let me use this to prove that the product of compact spaces is compact. Will I have time? Maybe not. So maybe let's stop here and I'll continue proving that the product of x and y, if x is compact and y is compact, then the product is compact. Okay, I'll do that on Friday, and I'll recall this tube lemma and maybe prove it. Okay, because it will take me like 6 or 7 minutes. Yeah. Okay. Any questions about the homework?